Welcome to our next video lecture. The basic topic for today's lecture is going to be conservation laws. So far, you've learned actually quite a lot in this course. You've learned everything that's necessary to understand anything that has to do with electric fields, including, for instance, the behavior of electrical circuits, how currents flow through a wire, resistance, all of those concepts. However, we're somewhat in a situation like you'll find yourselves in your first mechanics class, right? You start off with F equals ma. You learn that from just that one law, you have the power to understand all of the mechanical world around you. However, the course just doesn't stop there, and our course is not going to stop here. There's much more to the physical world than just the electric fields and the charges. And there's much more than just that simple description. What you find in your mechanics class, for instance, is that to get past F equals ma, you can just do everything with that, but it's going to make your life very difficult. You're going to be kind of crippling yourself. It turns out that there are some very powerful physical laws out there, the conservation laws, that allow you to do much more than you could do just with F equals ma alone. Now, there are three basic conservation laws that you learn about in mechanics class. The first two of them, conservation of angular momentum and conservation of momentum, it turns out don't play such an important role in electricity and magnetism, and in particular, the study of circuits. The reason for that is that the electric charges, particularly the electrons, are quite light. So their momentum and their angular momentum with their very low masses really don't enter very much into the consideration of what happens in electrical circuits. On the other hand, the third major conservation law that you learn about in your first mechanics class, the conservation of energy, plays a key role in the understanding of electric circuits. It's going to allow us, and we'll even see a quick example of that coming up very soon, it's going to allow us to address very quickly some very complex problems that can come up in circuits and give us a very good intuitive understanding of what is going on in a circuit context. So the basic topic for today's lecture is to really call back to mind and just begin to apply the basics of conservation of energy in the context of electricity and magnetism. Now, I'm going to begin by making contact with what you already know from mechanics class. So much of this actually is going to be a bit of a review. At least the beginning part will be. So let's review what we learn about conservation of energy in mechanics class. You learn very quickly that you can solve all kinds of challenging and interesting problems about, for instance, projectile motion and so forth, using a very powerful idea of the conservation of energy. We typically might write it down as saying that the energy of a problem is always constant, and that it's going to always be constant, and you'll be doing things like writing down the energy before a collision and the energy after, equating this constant thing, and then from that being able to solve your problems. The energy itself is typically broken down into kinetic energy components, which are in the form of, as you recall, 1/2 mv squared. But there's another component, right? The potential energy. Now, the potential energy you'll find is often written down in various ways depending upon the course that you take. Generally speaking, one is going to use a variable for potential energy. Typically, one might use the variable capital V. The difficulty for us, though, is capital V very quickly for us will become voltage. So we're going to use the other letter that's typically used in mechanics classes for the potential energy, and that is a capital U. So capital U will always represent potential energy for us, whereas capital V will be reserved for voltage. Now, this potential energy, though, is a function of the location of the particle. It's true that the kinetic energy, right, here is typically written in terms of the velocity of the particle, but the location of the particle is what generally controls the potential energy. So I'm going to write this as U here as a function of a vector location in three-dimensional space, x. Now, the question then quickly becomes, great, what is this magical potential energy function that we should add to the kinetic energy so that we get this nice law that the energy is always constant. That then takes us to our second concept from mechanics class, and that is known as work. So to kind of review what goes on with the concept here of work, I want to set up a situation. I will happen to make this an electrical situation, but the truth is in mechanics class it could be any type of a situation. But just to get us thinking about electricity and magnetism, let's imagine, for instance, I'll have three charges, Q1, Q2, and Q3, like so. And these guys now are going to be, and this is very important actually, they're going to be at fixed locations in space. They're just going to be nailed down. So I might, for instance, here I'll try to draw a little tack here that's nailing down my charge. Here's another tack nailing down this one, and this guy here is going to be nailed down. I just want to emphasize by doing this that these charges are fixed in location. They're not at all free to move. They are just nailed down right there. Now, with these fixed charges, I'm going to introduce another charge into the problem. This is the one I want to really understand its behavior. So I will call that charge here a capital Q. And the idea then is this charge capital Q is going to be moving throughout my space here. So it might have started out, for instance, at a vector location, which I will call A vector, right? And then it's going to follow some kind of a path. It's on its way, going between point A and then point B, which I will label up here. And my task, my goal is to understand the motion of this particle as he travels here along this path, say going from point A to point B. Now, the concept of work comes in when we begin to think about the amount of work, right, or energy that I would have to invest in order to move my particle Q along this trajectory from point A over to point B following this path. We typically will write down the work that's required to do that as W superscript us. This reminds us that this is the work done by us. As you will see coming up, it's important to keep track of who is actually doing the work. And we want to calculate here the work that it takes us to go from point A to point B. So as before, I like to write this little arrow here to indicate the idea we're going from A to B, right, along this prescribed path. And our job then is to calculate the work that we would have to do to carry that out. Now, we often might write this work in an abbreviated fashion as W sub BA, right? We might just skip, for instance, writing down the cute little arrow. That does help us keep our signs straight, as you'll see coming up. And then to compute that work, of course, what we're going to do is use the basic work formula. What the plan basically is going to be is we're going to divide this motion up into a series of little steps, a series of little vectors that are taking us along our path. Each little vector, as the particle Q is moving through these various different locations x, so x is the vector that's going to label the location of my particle, and as I go from one step here to the next step, right, my particle will have traveled this little displacement between these two locations here and here, and I will label that change in location a delta x. So then to calculate the total work done, what we would do is we would divide our path up into these little chunks, as I've indicated to you here, and I would then sum the work required to take me along each of those little steps, and that work, remember, is the force. And the force, of course, depends on the location of my particle as he's moving along his path. And the force also is a vector. Let's never forget that. And you may recall then that the formula for force, for work, is force times distance. So when we're at here location x and we're moving a distance delta x, we would multiply F times delta x. Delta x is a displacement, a vector that takes us from one point to another. And being a displacement, it is a vector, as I've indicated to you here. And now we have this issue that I've got two different vectors, a force vector and a position vector. We need to take some kind of a product. The product is going to be the type of product that gives us a scalar answer. Energy is not a vector. So the type of product that does that for us is actually the dot product. You may recall from your mechanics class that there's going to be a cosine of some angle theta. Just draw a little bubble here to remind us that this means there's going to be some kind of cosine theta that's going to be entering when we begin to think about that dot product. Now, the next thing I want to consider is what actual force goes in there. Well, if we're computing the work done by us, of course, then we had better apply then this formula to the force that we, F of us, right, that we are exerting on our particle. So let me sort of draw the diagram here, because there are two forces to consider, and this is where we have to keep things very straight to keep our signs appropriate. So imagine I'm at some point x here, again, along my path that's taking me from A towards B, and from now my particle, in my particular example here, but in any example, right, are going to be experiencing some forces from the rest of the system. In our case, the rest of the system consists of these external charges. So they're going to be exerting some force on my particle as he moves along the trajectory. So to indicate that, let me draw a force vector coming from the rest of the system. Just to make things simple, let's imagine all of our charges are positive, so then we know the force coming from the rest of the system would be some kind of repulsive force repelling from these objects, so that force would be maybe off in this direction. So that vector represents F, the forces that the particle would be feeling at location x. And we have to remember that for us to take the particle from A to B, the force we have to exert as we drag this particle kicking and screaming, right, from A towards B, fighting the external force F on the system, we would have to provide a force countering that repulsion so that we can keep our particle locked on its trajectory around that path. And this force then we would refer to as F us. Now, I know that sounds a little funny, but let's just stick with this as our standard notation. So that's the force that we are exerting at position x. And I think you can see very quickly how we can relate this to the actual force fields in the system, because the force from us has to be exactly counter to the force from the rest of the system, so that we can drag this particle very slowly here along his trajectory, countering the natural repulsive tendencies of the system maybe to just shoot our particle outwards. So the F us that appears here is actually minus the force F that the external system is exerting on our particle at location x. So now finally, to tidy this up, we can now see what our final formula will become. I'm going to be taking a sum over many tiny little displacements. So we realize very quickly this summation then is going to turn into an integral. So I'm going to have an integral. I want to write my integral in terms of the forces in my system. That would mean I would insert here, I'd substitute in this minus f of x. So I will write the f of x inside my integral, and I will take the opportunity to factor out that minus sign and pull it then out of the integral. The dot product, of course, stays the same thing as it always is, and the next major change is that the delta x here, right, the displacement in the limit of an infinitesimal displacement becomes a little infinitesimal dx. So we recognize what we have here from Math 1920 class, from vector calculus class, is going to be a line integral. And the integration proceeds from the starting point, which is this location A, and proceeds to the final point B. And that then would be my final formula for the work it takes us to take the particle from A to B. Very good. Now, there are a few considerations about this work law that turn out to have very important implications for circuits, as we will see coming up. So let's think a little bit and remind ourselves of the properties of this work function here, this calculation that we are carrying out. So let's look a little bit about the properties here of work. So the first thing I want to think about is how we can break down this work. So let's look at the work it takes to carry us from location to location B from location A. And let's just suppose for the moment that we actually have already calculated the work that's required to carry us from A to some third point, C, maybe the place where I draw in my force vectors. So imagine that point there was C. Now if I knew the work that it took to get me from A to C, and I knew then the work that it took to get me from C to B, I think then we know how to calculate the work from A to B, right? That would just be, if you think about it, the amount of work we first did to get us from A to C. So that would be W from A to C. And then we would simply have to add in the rest of the work as we went from C to B. So that would be the work from C. From C to B. So 2B from C. Now, this might seem like a very simple idea, but it turns out to be very powerful. There are actually only two key laws you need to analyze circuits. Those are called Kirchhoff's laws. The first one you've already learned about, which is that the current into a junction, into a region, has to match the current leaving the region. The second one is intimately related to this equation, as we will see coming up. This is very closely related to Kirchhoff's voltage law. And we'll see that as soon as we begin to relate this work to voltage. Okay, a second property we might ask ourselves about, which is very useful to keep in mind, is this interesting fact that the order really matters. If I look at the work instead of going from A to B, but thought about how much work it would take me to go from B and then track back to A, so I want to know the work now from B to A instead, you can see that, well, what I have to do is basically do the same summation in reverse order, which of course doesn't change the summation. But when I reverse my path and go from B to A, you'll notice all of my little displacement vectors are now pointing in the opposite direction. That would flip the sign on, here if I slide up just a little bit, that will flip the sign on my delta x's and would flip the sign then of the work I'm doing in each segment, and so I'd expect an overall minus sign to ensue. You'll notice also, if you just think about the definition of an integral, right? If I flip the order of integration, because now I'm going from B to A instead of from A to B, that's always associated with a change in the sign of the integral. So either way that you want to look at it, when I compute this work to take me from A to B, I can use the work, when I want the work from B to A, I can use the work W, right, to get me from A to B, and simply include a minus sign there. So it's very important that you keep in mind that actually the order here of these things matter. So the order of A and B matter. Very critical point there for you to keep in mind. Finally, I want to relate this to our initial discussion, and then we'll start to really apply these things in the electric field context. Our original discussion was in terms of this conservation law of energy. I had referenced the fact that we need to know what potential energy is, but we've just had this whole long discussion about work. What is the relationship then between the work and the potential energy? Well, the basic idea, of course, is that when we are putting work into the system, right, the work that we, us, put into the system, the whole idea is that if energy is conserved, and that's a big if, as we will see, but as long as energy is conserved, if I'm putting work into the system like this, that's energy, right, or work that I can potentially get back out. That's the concept behind potential energy. So if it turns out then that if energy is conserved And we'll see in a moment that that's the same idea as if saying that if the work it takes to get from B to A, or from A to B, either way you might want to look at it, the work from A to B, if that is path independent, and the point of that path independence, right, as you can see, would mean that, well, no matter how I decide to get from A to B, I need to have a special property of my force, so that if I take this pathway, I'll have a certain amount of work needed, or if I took this pathway, or any other path between those, I need this value of work from A to B to be completely constant or independent of path. If that's true, we have what is called a conservative force. And if the force is truly conservative, then you can show that the energy will always be conserved. And moreover, the quantity then that you need to include in your energy as this potential energy can be then defined as the potential energy at location X being equal to the work it takes to get you to point X from some standard reference point. You may recall when you do your trajectory problems in mechanics class that you're always dealing with this, the potential energy is mgh. It depends on the height, but your reference point of height is arbitrary. As long as you are always consistent with it, you will get the right answers. But you could say zero potential energy is the height at the bottom of the building if it's a projectile leaving a building, or it's the potential energy at the top of the building. You just need some reference point to define or to reference your work always back to. So we would write it like this, REF, or here I'll put it in, regular characters, REF, not in cursive, right? Just some reference point. If I think about the work it takes to get from my reference point to point X, because this work would be path independent, I don't have to worry about the path I'm taking, I will get something that is just a function of X. And that thing then that is the potential energy. It's the amount of work we could always get out of the system by taking our object from point X and then moving it back to our reference point. So these then are the key ideas from mechanics class that we're going to be building upon. I hope that all of these are relatively familiar to you. So our next step then is we're going to look at how we're going to apply these then to electric fields. So let's just slide ourselves up here a little bit.